people pass each other on a sidewalk, walking in opposite directions. They nod. They keep going. And in that ordinary instant, something impossible happens. The two of them no longer agree on what is happening right now, 2.5 million light-years away. For one of them, a decision made in a distant galaxy already lies in the settled past. For the other, that same decision has not yet been made. Same street, same second, different reality. Stay with me and you will understand why the word now, the most obvious, unshakable word you own, quietly falls apart the moment you look at it closely. You will see why the certainty of your past can be someone else's open future, changed by nothing more than a stroll in the other direction. We tend to think of the present as a single moment sweeping across the whole universe at once, one great cosmic clock ticking for everyone. It feels like the most solid thing there is. But the physics of the last century says that shared instant does not exist. There is only your slice, a thin sheet of moments you happen to call the present. And that sheet is tilted compared to everyone else's. Physicists sometimes call this the block universe, though a homelier name has stuck to it, the Spacetime Loaf. Imagine all of space and all of time baked together into a single solid object, and each observer cutting it at a slightly different angle. That angle is the whole story. Before this is over, you will see how the tilt arises, why your GPS would fail within a day if engineers ignored it, what a rotating universe does to the very idea of a shared present, and where the science stops and the honest mystery begins. If you find value in explorations like this, the subscribe button quietly helps these deep dives reach more curious minds. It costs you nothing and asks nothing back. So, here is where it begins. Start with the sidewalk, because everything else grows out of it. Two people, we will call them Alice and Bob, pass on a footpath here on Earth. Alice walks toward the constellation Andromeda. Bob walks away from it in the opposite direction. Their speed is trivial, an ordinary walking pace, roughly 1 meter per second, about 3.5 kilometers per hour, a little over 2 miles per hour. Nothing about them is exotic. They are not near a black hole. They are not aboard a spacecraft. They are two people on a sidewalk. The Andromeda galaxy, catalogued as Messier 31, sits about 2.5 million light-years away, around 765 kiloparsecs, which is roughly 2.4 times 10 to the 19th kilometers, or about 1.5 times 10 to the 19th miles. It is the nearest large spiral galaxy to our own, a faint smudge you can see with the naked eye on a dark night, its light having left it before our species existed. Now, here is the claim, and I want you to sit with how mild the ingredients are. Because Alice and Bob move in opposite directions, the set of events each of them regards as happening now over in Andromeda is different. Not by a fraction of a second, by days. If something were unfolding in Andromeda, a decision, an event, a departure, then relative to Alice's now, it might already have happened, while relative to Bob's now, at the very same instant on the sidewalk, it still lies in the future, undecided. The physicist Roger Penrose, who shared the 2020 Nobel Prize, gave this its vivid form. He imagined a fleet setting out from Andromeda and wrote that, according to one of the two people, an Andromedan space fleet has already set off on its journey, while to the other, the decision as to whether or not the journey will actually take place has not yet been made. According to one of them, he added, the decision lay in the uncertain future, while to the other, it lay in the certain past. Think about that for a moment before we go further. Take the time. Two people, walking at strolling pace, disagree by days about the state of a distant galaxy, and neither is wrong. There is no experiment either could perform to prove the other mistaken. Their disagreement is not an error. It is built into the structure of space and time. This is the phenomenon at the heart of everything we will explore, the relativity of simultaneity. In plain words, whether two separated events happen at the same time is not a fact about the universe. It is a fact about the observer. Change your motion even slightly, and you change your slice of now. Let me put a number on the Andromeda case, because the number is almost comically small. The offset in time between two observers' slices grows with three things: how fast they move relative to each other, how far away the distant event is, and the inverse square of the speed of light. Written out, the time offset equals the velocity times the distance divided by the speed of light squared. A named calculation by Fernandez-Rañada and colleagues works it through. At a walking speed of 1 meter per second, over the 2.5 million light-year distance to Andromeda, each walker's slice shifts by about 3 days of Andromeda's history. Two walkers, moving oppositely, therefore disagree by something on the order of days. 3 days of a galaxy's timeline purchased by turning around on a sidewalk. Consider what would have to be true for this to come out this way. The speed of light, c, is 299,792,458 meters per second. Call it 186,282 miles per second, and it is exact, a defined constant. That enormous number sits in the denominator, squared, which is why the effect stays invisible in daily life. But the distance to Andromeda is so vast that even a walking pace divided into that gulf resolves into days. The tininess of the tilt per meter and the vastness of the cosmic lever arm meet in the middle, and out comes something you cannot ignore. I return to this point often, not because it is comfortable, but because it is honest. The effect is not a trick of large speeds. It is always there. Every time you change direction, you retilt your entire slice of the universe. You do it constantly, unknowingly. And the only reason it never troubles you is that the things you care about are close, and closeness shrinks the offset to nothing. Out at cosmic distances, it blooms. To make sense of why any of this happens, we have to go back to how the idea took shape, and to the man who gave it its geometry. In 1905, working at a patent office, Einstein published his theory of special relativity, an account of how measurements of space and time relate between observers moving at constant velocity relative to one another. 3 years later, in September of 1908, in the German city of Cologne, before the assembly of German natural scientists and physicians, The mathematician Hermann Minkowski, who had once been Einstein's teacher at the Polytechnic in Zurich, stood up and recast the whole theory in a way that would change how physicists picture reality. Minkowski's move was to stop treating space and time as separate arenas and to weld them into a single four-dimensional structure: space-time. He opened with words that have echoed for over a century. "The views of space and time which I wish to lay before you," he said, "have sprung from the soil of experimental physics, and therein lies their strength. They are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Space and time, as separate things, fade into shadows. What survives is their union. This is where the loaf comes from. Take space, 3 dimensions, add time as a fourth, and treat the whole thing as one geometric object. Then the history of the universe is not a movie playing frame by frame. It is a finished shape. Every event that ever happens sits somewhere in that 4-dimensional block, at its own fixed location, past and future laid out together like a landscape. Picture a loaf of bread. The long axis running down its length is time. The cross-section at any point is all of space at one instant. Now take a knife and slice it. Each slice is a now, a complete 3-dimensional snapshot of the whole universe at a single moment. Stack the slices back up, and you have the history of everything. This is the image physicists use, and it carries a name from philosophy: eternalism, or the block universe. On this reading, past, present, and future are all equally real. The year 1908, this present moment, and a century from now, are all just different slices of the same loaf, no one of them more real than another. The now you feel so vividly is the slice you happen to occupy. Here is where the relativity of simultaneity re-enters, and where it becomes strange. The knife that slices the loaf can be held at different angles. An observer at rest slices it one way. An observer moving relative to them slices it at a tilt. Both cut the same loaf. Both slices are valid nows, but they are different slices, containing different events as simultaneous. Alice and Bob, on the sidewalk, hold their knives at very slightly different angles. And because Andromeda sits so far down the length of the loaf, those slightly different angles intersect the Andromeda region days apart. Consider a baker slicing a long loaf on a board. If she holds the knife perfectly upright, one slice. If she tilts it by a single degree, the blade still enters the top of the loaf at nearly the same place. But by the time it reaches the bottom of a very long loaf, it has moved far along its length. Small tilt at the near end, large displacement at the far end. That is precisely the geometry of the tilted now. Near you, the tilt costs almost nothing. 2.5 million light-years away, it costs days. Now, the mathematics that describes this tilt is worth stating plainly, because it is the engine of the entire subject. The relationship that governs how one observer's time coordinate relates to another's is called the Lorentz transformation, named for Hendrik Lorentz, with roots in the work of Henri Poincaré and its full meaning supplied by Einstein. In one direction, it reads, the new position equals gamma times the old position minus velocity times time. And the new time equals gamma times the old time minus velocity times position over the speed of light squared. The crucial piece is that last term. The new time depends not only on the old time, but on position. Move through space, and space bleeds into your measurement of time. That is the tilt, written as algebra. That factor, gamma, is the Lorentz factor, and it equals 1 over the square root of 1 minus velocity squared over the speed of light squared. When you move slowly, gamma is almost exactly 1, and the effects are negligible. As you approach the speed of light, gamma climbs toward infinity, and clocks, lengths, and simultaneity all warp dramatically. This single expression is why moving clocks run slow, why moving objects contract along their motion, and why now tilts. But the piece that matters most for us is the equation for simultaneity itself. The difference in time that one observer assigns between two events, as seen by another observer moving relative to them, equals gamma times the original time difference minus velocity times the spatial separation over the speed of light squared. Read that carefully. Even if two events happen at the same time in one frame, even if the original time difference is 0, the moving observer sees a time difference given by velocity times distance over light speed squared. Same events, different verdict on whether they were simultaneous. And notice that the offset scales with the spatial separation. The farther apart the events, the bigger the disagreement. That is why the sidewalk barely matters for things in the room and matters enormously for Andromeda. I want to be careful and fair here, because this is the point where the science is settled and the meaning is not. The relativity of simultaneity, the tilt itself, is not in dispute. It has been confirmed to extraordinary precision, and we will walk through the confirmations. What remains open, and what serious thinkers have argued about for a century, is what the tilt tells us about the nature of reality. Whether the loaf is truly a finished, static block, or whether the present is something more elusive that the block picture misses. We will return to this. Keep the loaf in mind, keep the tilt in mind, and keep one question filed away. Is the tilt a bare physical fact about the world, or partly an artifact of how we choose to set our clocks? That last question is not idle, and it takes us into the machinery of how now is even defined across a distance. Before you can say two distant events are simultaneous, you need a way to synchronize clocks that are far apart. And synchronizing distant clocks hides a subtlety that reaches all the way down to the foundations. Here is the problem. Suppose you have a clock here and a clock a kilometer away, and you want to set them to agree. You cannot simply look at both at once, because light takes time to travel between them. So whatever you see of the distant clock is already old. The natural fix is to send a light signal. You flash a pulse from your clock at a known time, it travels to the distant clock, bounces back, and returns to you. You measure the round-trip time. And then, here is the crucial step. You assume that the light took exactly half the round-trip time to get there and half to come back. You set the distant clock accordingly. This is Einstein synchronization, and it is the standard convention physicists use. But look at what you assumed. You assumed the one-way speed of light, the speed going out, equals the one-way speed coming back. That the light was neither faster on the way there, nor faster on the way back. It sounds obviously true, and yet it cannot be tested without first synchronizing the two clocks, which is the very thing you were trying to do. To measure the one-way speed, you would need two already synchronized clocks at the two ends. But synchronizing them requires assuming the one-way speed. The argument closes in a circle. This is the one-way versus two-way speed of light problem. And it is not a loose end that a cleverer experiment could tie off. It has been shown again and again that only the round trip, the two-way speed of light, is measurable without adopting a convention. The one-way speed, going in a single direction, cannot be measured without first assuming something equivalent to what you are trying to measure. Physicists have tried the obvious escape. Instead of flashing signals, take two clocks that agree and move one very slowly to the distant post, so slowly that any time dilation effect vanishes. This is slow clock transport. But it was proven that slow clock transport gives exactly the same synchronization as the light signal method, and it too quietly presupposes that the one-way speed is the same in all directions. The escape route leads back to the same room. The philosopher Hans Reichenbach turned this into a precise statement in the 1920s. He introduced a factor, epsilon, that can take any value strictly between 0 and 1, and wrote the time you assign to the distant clock as the departure time plus epsilon times the round-trip duration. Choosing epsilon equal to 1/2 is standard Einstein synchronization, the light takes equal time each way assumption. But Reichenbach argued that any other value of epsilon, anywhere in that open interval, produces a self-consistent description that predicts exactly the same observable results. The choice of 1/2, he held, is a convention, the simplest choice, but a choice. Think about what that would mean for the loaf. If the placement of the distant now involves a free choice, if you could, without contradicting any measurement, set that distant clock anywhere within a window defined by the light travel time, then part of the tilt of the now might not be a bare fact carved into space-time. It might be, at least in part, a byproduct of the ruler we chose. This is the conventionality of simultaneity thesis associated with Reichenbach and later with Adolf Grünbaum. And it will matter enormously when we come to weigh what the block universe really requires. I have to be even-handed because this thesis did not go unchallenged. In 1977, the philosopher of physics David Malamud proved a theorem that many read as cutting against conventionality. Malamud showed that if you demand a simultaneity relation definable purely from the causal structure of spacetime relative to a single inertial observer, with some natural requirements, then standard synchronization, epsilon equals 1/2, is the only non-trivial option that qualifies. Once you accept his assumptions, the conventional freedom collapses and the standard choice is forced. Malamud's theorem is widely cited as the strongest case against conventionalism. But it too was contested. Grunbaum and Alan Janis argued that one of its assumptions, that the simultaneity relation must be an equivalence relation, neatly partitioning events into tidy classes, is exactly what a conventionalist need not grant. So the matter did not close. It narrowed, and it stayed alive. Keep this tension in mind. We will return to it when we ask how much of the loaf is real geometry and how much is bookkeeping. There is a way to make the synchronization problem tangible, and it involves rotation. Picture a ring, a loop of optical fiber, or a circular path for light, and send two light beams around it in opposite directions, one clockwise, one counterclockwise, and let them meet again where they started. If the ring is not rotating, they arrive together. But if the ring rotates, the beam traveling in the direction of rotation has to chase a moving finish line, while the beam going against the rotation meets it coming toward it. They arrive at slightly different times. And when you recombine them, the light waves interfere and produce a measurable shift. This is the Sagnac effect, and it was demonstrated by Georges Sagnac in 1913 with a rotating ring interferometer on a laboratory table. The size of the effect follows a clean formula. The phase shift equals 8 pi times the enclosed area times the angular velocity, divided by the wavelength times the speed of light. The larger the area you enclose, and the faster you spin, the bigger the shift. Sagnac himself misread his result as evidence for a stationary ether, a fixed medium for light. But modern physics accounts for it completely within relativity applied to a rotating frame. What the Sagnac effect shows, tangibly, is that on a rotating platform, you cannot consistently synchronize clocks all the way around the loop. Try to set every clock around the ring using light signals, and when you come back to where you started, you find a discrepancy that will not close. The synchronization path itself matters. The abstract subtlety about defining now becomes a physical fringe shift you can photograph. In 1925, Albert Michelson, George Gale, and their collaborators scaled this up enormously. Near Clearing, Illinois, they built a giant rectangular ring interferometer, a loop of evacuated pipe with sides of 612 by 339 meters, roughly 2010 by 1,113 feet, a perimeter of nearly 2 kilometers, about 1¼ miles. Their goal was audacious: to detect the Sagnac effect produced by the rotation of the Earth itself. They sent light around that vast rectangle in both directions and looked for the fringe shift Earth's spin should produce. They measured a shift they reported as 230 parts in 1,000, against a prediction of 237 parts in 1,000. Agreement within about 2%. The planet's own rotation, written into the interference of light beams a fifth of a mile apart. A century later, reviews of the original data confirm the agreement holds to within a couple of percent. What does it mean that the way we cut the loaf into slices depends, in part, on conventions and on the state of motion of our clocks? And yet, the world still hangs together into a single, consistent geometry. Hold that question. It is one of the threads we will pull hardest at the end. Because underneath all these frame relative slices, there is something every observer agrees on. This is the part that first made me stop and sit quietly with the theory. However differently Alice and Bob slice the loaf, however they set their clocks, there is one quantity they compute identically: the space-time interval. It is captured in the Minkowski line element, the geometric heart of the whole structure. Written out, the interval squared equals minus the speed of light squared times the time separation squared plus the spatial separation squared in each of the three directions of space. That minus sign in front of the time term is everything. It distinguishes time from space in the geometry, and it makes space-time not simply four-dimensional space, but something with a built-in causal grain. Here is why it matters. Two observers moving relative to each other will disagree about how much time elapsed between two events, and disagree about how much space separated them. But when each of them plugs their own numbers into that expression, combining their time and their space with that minus sign, they get the identical answer. The interval is invariant. It is the objective bone beneath the frame-relative flesh. The slices tilt, the loaf does not. Consider two surveyors sent to map the same tower from different angles. One says the tower's shadow stretches 30 meters east and its height contributes 10. Another, standing elsewhere, divides it differently between along my line of sight and across it. They disagree about the breakdown. But if they each compute the tower's true length from their own components using the right geometry, they agree exactly on the length. The tower has not changed. Only their coordinate systems have. Space and time, in relativity, are like the surveyor's east and north. How you split the interval between them depends on your motion, but the interval itself is the real shared thing. This is what Minkowski meant by saying only the union preserves an independent reality. This is the part that stays with me. Not the disagreement, but the agreement underneath it. The universe permits every observer their own tilted now, their own division of the loaf, and yet forbids any real contradiction, because they are all cutting the same invariant object. The freedom and the constraint are woven together so tightly that no two observers can ever be brought into genuine conflict about a physical fact. They can disagree about when and where, but never about the invariant interval and never about the order of events that can influence one another. That last clause is critical, and it protects us from paradox. Events that can causally affect one another, where a signal traveling at or below light speed could pass from one to the other, are never reordered by any observer. Everyone agrees on their sequence. The reshuffling of now only ever touches events that are causally disconnected, too far apart in space, too close in time, for any light signal to bridge them. In the language of the theory, these are space-like separated events, lying in each other's elsewhere, outside each other's light cones. The Andromeda decision and the sidewalk are space-like separated. No light, no signal, no influence could pass between them in the relevant window. And that is exactly why Alice and Bob can disagree about their simultaneity without any contradiction ever surfacing. Nothing that happens in Andromeda now can reach the sidewalk now. So their disagreement has no operational teeth. It cannot send a message, cannot be caught in a lie, cannot be resolved. It simply stands. The light cone is worth picturing directly. Imagine sitting at an event, a point in space-time, here and now. Draw the paths that light could take away from you into the future. They sweep out a cone opening upward, the future light cone, containing everything you could possibly influence. Draw the paths light could have taken to reach you, a cone opening downward into the past, containing everything that could possibly have influenced you. Everything inside those cones is causally connected to you. Everything outside, the vast region to the sides, is the elsewhere, causally cut off. And it is precisely there that different observers' nows disagree. Your world line, the track of your whole life through space-time, threads up through the tip of each successive light cone, always staying inside the causal structure. Now let us leave the sidewalk and Andromeda for a while, because the tilted now is not a philosopher's abstraction. It runs right now inside a machine in your pocket. And walking through that machine will show us that the loaf is not merely a way of talking. It is engineered into technology that would fail without it. Consider the global positioning system. High above your head, roughly 20,200 kilometers up, about 12,550 miles, a constellation of satellites orbits the Earth, each completing 2 orbits a day, moving at about 3.9 kilometers per second, near 2.4 miles per second. Each carries an atomic clock. Your receiver figures out where you are by comparing the timing of signals from several satellites at once. A timing error of a billionth of a second translates to about a foot of position error. The whole system is, at bottom, a way of slicing space-time precisely enough to locate you on the Earth's surface. And here, the 2 great effects of relativity pull in opposite directions. Because the satellites move fast relative to the ground, special relativity says their clocks run slow, the kinematic effect, losing about 7,210 nanoseconds per day, roughly 7 microseconds. But because they orbit high up, where the Earth's gravity is weaker, general relativity says their clocks run fast, gravitational time dilation, gaining about 45,650 nanoseconds per day, about 46 microseconds. The gravitational speed-up wins. The net effect is that each satellite clock runs fast by about 38,440 nanoseconds per day, call it 38 microseconds, relative to a clock on the ground. The combined rate is captured compactly. The fractional shift in clock frequency equals the gravitational potential difference divided by the speed of light squared minus 1/2 the velocity squared over the speed of light squared. The first term is the gravitational gain. The second is the kinematic loss. Plug in the altitude and orbital speed, and out comes that net fractional rate of about plus 4.465 times 10 to the minus 10th. The engineers of the system knew this before it launched. They did not correct the clocks in software after the fact. They physically detuned them before flight, setting each satellite's oscillator to run at 10.2299999543 MHz instead of the round 10.23 MHz, so that once in orbit, dilated by motion and lifted by weaker gravity, they would tick at the right rate as seen from the ground. Now imagine what happens if you ignore all this. 38 microseconds a day sounds like nothing. But light travels about 30 centimeters, a foot, in a nanosecond. And 38 microseconds is 38,000 nanoseconds. Left uncorrected, the position error would accumulate at roughly 11 kilometers per day, about 7 miles. Within a single day, the system would be useless. Within hours, badly wrong. Every time your phone tells you which street you're on, it silently honors the relativity of time. The fact that clocks at different speeds and different depths in gravity tick at different rates, and that now for the satellite is not now for you. There is one more layer, and it brings us straight back to the Sagnac effect. The Earth rotates, and the GPS reference frame rotates with it. A signal traveling around the globe in the direction of rotation and one traveling against it do not take equal times, exactly as with Sagnac's ring. The correction for this, the Sagnac correction, can reach about 207 nanoseconds near the equator, equivalent to some 30 meters of position, about 100 feet. The abstract impossibility of consistently synchronizing clocks on a rotating platform, which we met as a laboratory fringe shift, is here a routine line of code that keeps aircraft on their approach paths. The tilted, rotation-dependent now is load-bearing infrastructure. I find this the most grounding fact in the whole subject. You can debate the metaphysics of the block universe forever, but the relativity of time is not debatable. It is validated billions of times a day in every navigation fix on Earth. When people say relativity is just a theory, this is the quiet rebuttal. The theory is holding up the modern world. The direct experimental confirmations are worth walking through, because they turn the sidewalk thought experiment into laboratory fact. In 1971, the physicists Joseph Hafele and Richard Keating did something wonderfully literal. They took 4 cesium beam atomic clocks, bought them their own airline seats, and flew them around the world, once eastward, once westward. Then compared them to reference clocks at the United States Naval Observatory. Relativity made specific quantitative predictions. The eastward flying clocks, moving with Earth's rotation, should lose time relative to the ground. The westward clocks, moving against it, should gain. The prediction for eastward was a loss of about 40 nanoseconds. For westward, a gain of about 275 nanoseconds. The measured results: eastward, a loss of 59 nanoseconds. Westward, a gain of 273 nanoseconds. both matching the combined predictions of special and general relativity within the experimental error. Clocks flown on ordinary commercial jets came home disagreeing about how much time had passed, exactly as the theory said they must. What does it mean that two clocks set together, flown around the planet in opposite directions, and brought back to the same room no longer agree? It means the tilt is not a way of speaking. It is a measured difference in elapsed time, catalogued, published, and reproduced. Time itself is not the universal backdrop we feel it to be. Now we go deeper, because so far we have only tilted the slices by motion. Gravity does something more violent. It does not merely tilt the loaf slices, it curves them, bends them, and in extreme cases threatens to tear the loaf apart entirely so that it cannot be sliced at all. General relativity, Einstein's 1915 theory of gravity, describes mass and energy as curving space-time. The curvature is encoded in a mathematical object called the metric, which tells you how to measure intervals near a given distribution of mass. For a non-rotating spherical mass, the relevant solution is the Schwarzschild metric, found within months of Einstein's field equations. Its structure contains a telling factor, the square root of 1 minus the ratio of the Schwarzschild radius to your distance from the center. The Schwarzschild radius is the size of the event horizon, the point of no return for a given mass. As you approach it, that square root shrinks towards zero. Clocks slow without bound. To a distant observer, a clock falling toward a black hole ticks slower and slower, its light stretched redder and redder until, at the horizon, it appears to freeze entirely. The now of the infalling clock and the now of the distant watcher come apart without limit. Picture a beacon dropped toward a black hole, flashing once per second by its own reckoning. To someone watching from far away, the flashes arrive further and further apart, every 2 seconds, every 10, every hour, every year, the intervals stretching toward infinity as the beacon nears the horizon, its light sliding from white to red to invisible. The beacon in its own frame keeps flashing steadily and falls right through. Two utterly different accounts of the same object's now, and gravity is what pried them apart. Now let the mass rotate, and something even stranger appears. A spinning mass does not just curve space-time, it drags it around with itself, like a spoon turning in honey. This is frame dragging, predicted in 1918 by the Austrian physicists Josef Lenzer and Hans Thirring, and often called the Lenzer-Thirring effect. The metric for a rotating black hole, the Kerr metric, found by Roy Kerr in 1963, contains an off-diagonal term mixing time and the angular direction. That mixing is frame dragging written in geometry. Near a rotating mass, the very definition of standing still is swept around with the rotation. The local now is not neutral, it is dragged. This is not speculation. In 2004, NASA launched Gravity Probe B, a satellite carrying 4 gyroscopes machined into the most perfect spheres ever made, cooled to near absolute zero, floating in a polar orbit about 642 kilometers up. The idea was to let those gyroscopes point at a fixed star and watch whether the curvature and dragging of space-time around the spinning Earth slowly tilted their axes. Two effects were predicted. The geodetic effect, the tilt from the Earth's mass curving space-time, was predicted at 6,606 milliarcseconds per year and measured at 6,601.8, give or take 18.3. And the far tinier frame dragging effect, the Earth's rotation itself dragging space-time around, was predicted at 39.2 milliarcseconds per year and measured at 37.2, give or take 7.2. A milliarcsecond is the width of a human hair seen from 10 miles away. The Earth, turning, drags the fabric of space-time with it, and we have measured the drag. Complementary tests come from satellite laser ranging, bouncing lasers off passive spheres like the Lagios satellites and the Lares satellites, tracking how their orbits are slowly twisted by the same frame dragging of the rotating Earth, confirming the effect to within a handful of percent. Different technique, same conclusion. A rotating mass drags the local standard of rest and with it the local now. And now to the deepest case, the one that shows the loaf can lose its slices altogether. In 1949, for Einstein's 70th birthday, the logician Kurt Gödel, Einstein's close friend at Princeton, presented an exact solution to the field equations of general relativity. Gödel constructed a universe, rotating, uniformly filled with matter, with a particular value of the cosmological constant. And this universe had a monstrous property. Beyond a certain radius, the loops that circle around through space become time-like, which means an observer could travel along one of them and return to their own past. These are closed time-like curves. In Gödel's universe, time travel into the past is not forbidden by the equations, it is permitted by an exact solution of them. The consequence for the loaf is profound. In our familiar picture, you can at least imagine stacking the slices in order. This now, then the next, even if different observers tilt them. But in Gödel's universe, there is no consistent way to stack them at all. You cannot slice the loaf into a global sequence of nows, because the timelines curl back on themselves. Any attempt to lay out a universal before and after collapses into contradiction. The Gödel universe cannot be foliated, cannot be cut into a clean stack of spatial slices ordered by time. The loaf, in his solution, has no coherent way to be sliced. Now, our universe does not appear to be a Gödel universe. It is not rotating in the required way, and no closed time-like curves have ever been observed. But that is not the point that shook people, and it is the point I want you to sit with. The point is that Einstein's own equations, the most successful theory of gravity we have, do not, by themselves, forbid such a universe. The equations permit solutions in which the global now simply does not exist as a coherent concept. Whether nature actually excludes such solutions, and by what mechanism, is an open question in physics. Some physicists suspect an as-yet unknown chronology protection principle in a future theory of quantum gravity would rule them out. But as of now, the equations are more permissive than our intuition, and the loaf is, in principle, sliceable only in a universe cooperative enough to allow it. This machinery of slicing has a formal home in general relativity, worth naming because it makes the loaf mathematically precise. It is called the ADM formalism, after Arnovit, Deser and Meissner, a way of rewriting Einstein's four-dimensional theory as a three-dimensional space evolving through time, a 3+1 split. Its line element introduces two quantities: the lapse, which tells you how much proper time elapses between one slice and the next, and the shift, which tells you how the spatial coordinates slide from slice to slice. In this picture, space-time literally is a stack of spatial slices, the loaf, cut and restacked, with the lapse and shift describing how the knife moves. This is not a metaphor imposed from outside. It is one of the standard ways physicists actually formulate gravity, and it is the mathematical backbone of numerical relativity, the field that simulated the merging black holes whose gravitational waves LIGO detected in 2015. That detection deserves its moment because it drives home what space-time is. On the 14th of September 2015, the two LIGO observatories caught a ripple passing through the Earth, a gravitational wave from two black holes spiraling together over 1 billion light-years away. Space-time stretched and squeezed by less than the width of a proton across a 4-kilometer arm, and we heard it. What LIGO proved is that space-time is not an inert stage on which events play out. It is dynamical. It bends, it ripples, it carries energy. The loaf is not a fixed table. It is a medium that flexes. And a medium that flexes is a medium whose slices are not simple. Now I want to turn to the quantum world, because it introduces a tension that the clean geometric picture of the loaf does not comfortably absorb. And this is a thread we will pull hardest at the end. In 1964, the physicist John Bell, working at CERN, proved a theorem of startling reach. He considered pairs of particles prepared together and then separated, and asked what correlations their measurements could show if the world obeyed two reasonable-sounding assumptions: that the particles carry definite properties independent of being measured, and that no influence travels faster than light between them. Bell derived a precise limit, a number that such local realistic correlations could not exceed. The quantum mechanical prediction violated that limit. The world, quantum mechanics said, is correlated more tightly than any local predetermined arrangement allows. The precise form is the CH-SH inequality, built from measurements at different settings on the two particles. For any local realistic theory, a certain combination of correlations, called S, cannot exceed 2. Quantum mechanics predicts it can reach up to 2 times the square root of 2, about 2.83, the Tyrrellson bound. The gap between 2 and 2.83 is the quantitative border between a world of local, pre-existing properties and the world we actually inhabit. For decades, this was tested with ever tighter experiments, closing loopholes, subtle ways a local theory might have mimicked the quantum result. In 2015, 3 groups achieved loophole-free violations. At Delft, a team led by Ronald Hansen used nitrogen vacancy centers in diamonds separated by 1.3 kilometers and measured S equal to 2.24, give or take 0.20, with the probability of a fluke around 4%. In Vienna, Anton Zeilinger's group, and at NIST, Christa Scharm's group, pushed the statistical confidence to staggering levels. In Vienna, the probability that local realism could have produced the data was around 3 × 10 to the minus 31. In 2022, the Nobel Prize in Physics went to Alain Aspect, John Clauser, and Anton Zeilinger, in the words of the committee, for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Here is why this troubles the loaf. When you measure one particle of an entangled pair, the correlated outcome of its distant partner is fixed instantaneously in a manner that no local slicing of spacetime seems to accommodate. The correlation does not respect the neat separation of causally disconnected regions. And yet, and this is essential, you cannot use it to send a signal. The individual outcome at each end looks completely random. Only when the 2 records are later brought together and compared does the correlation appear. This is the no signaling theorem, and it is what keeps quantum non-locality from contradicting relativity outright. No message travels faster than light. No paradox erupts. But something non-local is unmistakably present in the correlations. What does it mean that the world is stitched together more tightly than any local arrangement of the loaf's slices would permit, yet stitched in a way that can never be used to send a message, never caught contradicting relativity? Bell himself was uneasy. He wrote that it may well be that a relativistic version of the theory, while Lorentz invariant and local at the observational level, may be necessarily non-local and with a preferred frame, or ether, at the fundamental level. A preferred frame, a hidden now beneath the surface, undetectable but real. That is a striking thing for a careful physicist to suspect, and it is a seed we will harvest later. I want to introduce the interpretations that try to live with this, because they will be among the explanations we weigh. One is relational quantum mechanics, developed by Carlo Rovelli in 1996. On this view, there is no absolute, observer-independent state of a system. Physical quantities have values only relative to the systems they interact with. There is, in Rovelli's phrase, no view from nowhere. Applied to time, this dissolves the demand for a single true now. Facts are relational, and the frame dependence of the tilted now is not a puzzle, but the expected shape of a relational world. Rovelli puts the temporal version bluntly. The present of the universe, he writes, is meaningless. And elsewhere, our present does not extend throughout the universe. It is like a bubble around us. He sharpens it with an analogy I found genuinely disarming. Compare now with here, he says. No one would dream of insisting that things here exist while things elsewhere do not. Here is just where the speaker stands. Why then do we insist that things now exist while things at other times do not? If now is like here, an indexical, a pointer that depends on who is speaking and where they stand in the loaf, then the felt specialness of the present may be a fact about us, not about the universe. Another interpretation runs in the opposite temporal direction. John Cramer's transactional interpretation from 1986 treats a quantum event as a kind of handshake across time. An emitter sends an offer wave forward in time. An absorber sends a confirmation wave backward in time. Where they reinforce, a transaction completes, and a quantum of energy changes hands. It is explicitly non-local and relativistically symmetric, and it takes the time symmetry of the underlying equations at face value, treating the future as participating in the present in a way our forward-flowing intuition resists. Whether or not it is correct, it illustrates how seriously the block picture's time symmetry can be taken. And at the far edge sits Julian Barber's proposal from his 1999 book that time does not fundamentally exist at all. Barber argues that reality is a vast, timeless collection of static configurations. He calls it Platonia, each a complete now, and that the sense of flow arises because each configuration contains records, memories, apparent traces of others, giving the illusion of a sequence. He points out that general relativity, cast in the ADM form and pushed toward quantum gravity, yields the Wheeler-DeWitt equation, in which the time variable drops out entirely. If Barber is right, the loaf is not merely static. Even the stacking is an illusion, and there is only an unordered heap of nows. Before we weigh anything, one more empirical thread, because it complicates the very idea of a cosmic standard of rest. Special relativity insists no inertial frame is physically privileged. And yet, cosmology hands us something that looks like one. The cosmic microwave background, the faint afterglow of the early universe, mapped by COBE, WMAP, and the Planck satellite, is almost perfectly uniform across the sky, but not quite. It shows a dipole, slightly hotter in one direction, cooler in the opposite. The standard reading is that this dipole is a Doppler shift caused by our own motion. From it, we infer that the solar system moves at 369.82 kilometers per second, about 229.8 miles per second, toward a specific point in the sky, with a precision of about 1/10 of a kilometer per second. This gives us a practical cosmic rest frame, the frame in which the dipole vanishes, in which the universe looks isotropic. It is a standard of rest for the cosmos, even though relativity forbids any frame from being fundamentally special. That tension has usually been treated as harmless. The CMB frame is picked out by the matter content of the universe, not by the laws, so no principle is violated. But recently, the harmony has cracked. And this is a live, unresolved observation I want on the table. If our motion relative to the CMB is real, it should produce a matching dipole in the counts of distant galaxies and quasars, more of them appearing in the direction we move by a predictable amount. In 2021, Nathan Seacrest and colleagues measured this number count dipole using well over 1 million distant quasars and found it over twice as large as expected and offset by some 27 degrees from the CMB dipole's direction, rejecting the simple kinematic interpretation at the 4.9 sigma level. A Bayesian reanalysis in 2023 found the amplitude about 2.7 times the kinematic expectation at 5.7 sigma. And a 2025 study combining radio surveys reported the dipole about 3.67 times larger than expected, a 5.4 sigma discrepancy. These are not marginal hints. They are a genuine tension over whether the CMB frame really is the cosmic rest frame, and over whether the universe is as isotropic as the standard model assumes. What does it mean that the one frame we treat as the universe's standard of rest may not agree with itself when measured two different ways? File it away. It bears on the deepest question of all, whether there is anywhere a now that the universe itself prefers. For the past while, I have laid out the evidence and the interpretations without judging between them. The tilted now, the conventionality of synchronization, the invariant interval, the engineered corrections in GPS, the flown clocks, the dragging of spacetime by rotating mass, the equations that permit a universe with no global now at all, the quantum correlations that ignore the slices, the interpretations that try to absorb them, and the cosmic frame that may not be as clean as we thought. Now we turn to the harder task. Now we see which explanation the evidence actually supports and where each one strains. Start with what is not in doubt, because it anchors everything else. The relativity of simultaneity is real. This is not an interpretation, it is measurement. Hafler and Keating flew clocks around the world and brought them home disagreeing within the predicted margins. GPS satellites drift 11 kilometers a day if their relativistic detuning is ignored, and they do not drift because the correction is built in and works. Gravity Probe B measured the Earth dragging spacetime around itself to milli-arcsecond precision. The tilt of the now, the curvature of the slices, the dependence on motion and gravity, all of it is confirmed to as many decimal places as we care to measure. Whatever we conclude about the deeper nature of time, it must be consistent with these facts. Any picture of now that requires the tilt to be an error is already refuted. So the question is never whether the now tilts, it is what the tilt means. And here the competing pictures line up. The block universe, eternalism, is the physicist's working default, and it has real evidential weight. It is the cleanest fit with the symmetry of special relativity. If no frame is privileged and every observer's tilted slice is as valid as any others, then the simplest ontology is one in which all the slices are equally real, the whole loaf, past and future, together. This is the reading Minkowski's geometry invites, and it is the one the Reitdijk-Putnam argument makes explicit. Since each observer's plane of simultaneity defines a present, and observers in relative motion have differently tilted planes, and each present is taken to be equally real, then reality must include all of them, the entire four-dimensional block. Einstein himself, consoling a grieving family in 1955, wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. Where does the block picture hold? It holds wherever relativity holds, which is everywhere we have looked. It is consistent, it is elegant, and it makes the tilted now unmysterious. Of course, observers disagree about which slice is now, if all the slices are equally real and now is just an index. Where does it strain? In three places. First, it offers no account of the vivid experience of flow, of the present feeling special, of time seeming to pass. It can call that an illusion, as Einstein did, but calling it an illusion is not explaining it. Second, it must square with quantum measurement, with the fact that outcomes seem to become definite, which sits awkwardly in a world where all events already, timelessly, are. And third, this is the crucial one. The inference from relativity to the block is not actually forced. That third point is where I have to be scrupulously fair, because it is the most important correction to the naive story, and it is often left out. In 1968, and again in 1991, the philosopher of physics Howard Stein proved something that constrains the whole Reitdijk-Putnam argument. Stein asked, what is the only relation of definiteness or becoming you can define on Minkowski spacetime that respects the theory's own symmetries, that is, Lorentz invariant and logically well-behaved? And he proved that the answer is not a global slice at all. The only such relation is strictly local. At a given point, the events that are definite or settled relative to it are exactly those in its causal past, inside its past light cone, and nothing else. Not a tilted global plane, a point. Sit with what Stein showed, because it quietly dismantles the forced march to the block. The Reitdijk-Putnam argument needs each observer's now to be a global slice, extending out to Andromeda, equally real all along its length. But if you demand that the present respect relativity's own symmetries, the only consistent notion of present is here and now, strictly local, the tip of your light cone. There is no relativistically privileged global slice to be real. And if there is no privileged global slice, the argument that all the slices are real, therefore the whole block is real, loses its first premise. The block universe may still be true, but it is not compelled by special relativity. It is a philosophical reading laid on top of the geometry, not a theorem forced by it. Earlier, I said we would return to the question of whether the tilt is a bare physical fact or partly a convention. Now we do. Recall Reichenbach and Grunbaum. The one-way speed of light is not measurable without a synchronization convention, and standard synchrony, epsilon equals 1/2, is a choice, the simplest, but a choice. If that is right, then part of where the distant now falls is not carved into the world, it is set by our ruler. And that further weakens the claim that the tilted slices are hard physical facts about reality rather than partly conventions of description. But I promised even-handedness, and Malamont's 1977 theorem pushes back. Given his assumptions, standard synchrony is the only choice definable from the causal structure. And Grunbaum and Yanis pushed back on Malamont, questioning whether one of his assumptions should be granted. Where does this leave us on the evidence? In an honest middle. The two-way speed of light is a hard fact. The one-way speed, and thus the exact placement of the distant now, carries a residue of convention that a century of argument has narrowed but not eliminated. The tilt is real. How much of its detailed geometry is world, and how much is bookkeeping, is not fully settled. Now, presentism, the view that only the present exists, that the flowing now is the whole of reality. It has the advantage of matching experience. It says the present feels special because it is special, the only thing that is real. Where does it hold? Nowhere in the physics without a cost. To maintain a single objective present against the relativity of simultaneity, the presentist must posit a preferred frame, a true now that the theory hides from us. William Lane Craig has developed exactly this, a neo-Lorentzian view in which absolute simultaneity exists but is undetectable because motion physically distorts our rods and clocks in just the way that mimics relativity. Ned Markosian distinguishes the bare, confirmed physics from a metaphysically loaded version and argues the anti-presentist argument smuggles in the loaded one. Dean Zimmerman argues a privileged present can ride atop relativistic structure without contradicting any measurement. Where does presentism strain? Precisely on that preferred frame. To save the flowing now, it must postulate a distinguished slicing of space-time that no experiment can detect, and now the universe uses but never reveals. Yuri Balashov and Michel Janssen argue forcefully that this is explanatorily inferior. The space-time picture explains why no frame is detectable by saying none is privileged, whereas the neo-Lorentzian view must explain the same fact by an elaborate conspiracy of undetectable distortions. On grounds of parsimony, the block-style reading wins. But, and here the threads begin to braid, presentism's demand for a preferred frame is not as isolated as it once looked, because Bell, from an entirely different direction, suspected the very same thing. This is where the quantum thread pays off. Recall Bell's own words. A deeper theory might be necessarily non-local and with a preferred frame, or ether, at the fundamental level. Recall the loophole-free experiments of 2015 and the 2022 Nobel. The correlations of entangled particles are real, confirmed to 31 decimal places of confidence in Vienna, and they do not fit into the neat local slicing of the loaf. The interpretations that take non-locality most seriously, Bohmian mechanics with its guiding wave, and the GRW flash models with their objective collapse events, tend to require, or run most naturally with, a preferred foliation of spacetime, a hidden now. The same preferred frame the presentist wants for the flow of time, the Bohmian may want for the trajectories of particles, and Bell suspected for the structure of non-locality. Weigh this carefully, because it is the most interesting convergence in the whole subject, and also the place where the evidence refuses to hand us a clean verdict. On one side, manifest Lorentz invariance. Every direct test, the standard model extension bounds, the timing of gravitational waves across the sky, decades of particle physics, shows no preferred frame to staggering precision. The surface of the world is Lorentz invariant through and through. On the other side, quantum non-locality is real, and it sits uneasily on that surface. And careful physicists from Bell onward have suspected a preferred frame hiding underneath. And no signaling is the razor's edge between them, the reason the tension has never become a contradiction. You cannot send a message with entanglement, so the preferred frame, if it exists, is undetectable, exactly as the presentist's preferred frame is undetectable, exactly as Bell said an ether at the fundamental level would be. Here is where the evidence actually leaves us, stated plainly. The relativity of simultaneity is a confirmed physical fact. The tilt is real, engineered into GPS, flown on airplanes, measured in the dragging of space-time around the Earth. The block universe is the cleanest interpretation of that fact and the working default. But it is not forced. Stein proved that relativity's own symmetries support only a local, point-like present, not a real global slice. So the march from the now tilts to the whole loaf is equally real is a philosophical step, not a theorem. Presentism can be maintained, but only at the price of an undetectable preferred frame that most physicists judge explanatorily extravagant. And yet, remarkably, quantum non-locality and Bell's own suspicion point toward the possibility of just such a hidden frame from an entirely different direction, so the option cannot be dismissed. Conventionalism captures something true. The one-way speed of light is not measurable, and part of the now's placement is convention, but is constrained by Malamont's theorem into a narrower claim than its founders hoped. And the relational and timeless pictures, Rovelli's "The present of the universe is meaningless," Barber's timeless Platonia, dissolve the problem rather than solve it, trading the puzzle of the now for the puzzle of why anything seems to change at all. So what is now? The science tells us with total precision how it behaves, how it tilts, curves, drags, and refuses to be global. It tells us there is no single instant shared across the universe, that your slice and mine differ, that at cosmic distances the difference reaches days, that in a rotating universe the very idea of a global slice can fail, that beneath the tilting surface lies an invariant geometry all observers share. What the science does not tell us, what it cannot yet settle, is what the present is. Whether it is the whole static loaf laid out complete, whether it is a growing edge with the past fixed and the future genuinely open, whether it is only ever the local here and now that Stein's theorem allows, whether it is a relational bubble around each observer, or whether now is, like here, a pointer that says more about us than about the universe. This is the honest edge, and I will not paper over it. Physics has mapped the behavior of time to extraordinary depth and left the nature of the present open. The evidence constrains every answer and forces none. It rules out a naive universal now. It does not tell us whether becoming is real or whether the future already, timelessly, is. And there is one more open question sitting quietly beneath all the others, the one I ask you to file away. Even the frame we treat as the universe's own standard of rest, the cosmic microwave background, may not agree with itself. The number count dipole from distant quasars and radio sources comes out 2 to nearly 4 times larger than the motion-only prediction at more than 5 sigma. If that tension is real, and not some undiagnosed systematic, then the one candidate for a cosmic now, the frame in which the universe looks the same in all directions, is under strain from the data itself. The universe may not hand us the preferred slice that both the presentist and the Bohmian would like to borrow. When I first understood all this, I had to sit with it for a while. Not because of the strangeness, but because of the precision. The universe permits every observer their own tilted now, refuses any of them a universal one, forbids them all from ever catching each other in a contradiction, and stitches the whole thing together with an invariant interval so exact that navigation satellites keep time by it. That is not chaos. That is not a free-for-all. It is a structure of astonishing tightness that nonetheless declines to tell us the one thing we most want to know: what the present, the thing we are living in this very second, actually is. Let me bring this exploration to a close. We began on a sidewalk, with 2 people passing in opposite directions and disagreeing, by days, about the state of a galaxy 2.5 million light-years away. From that single, ordinary image, we followed the tilt down into its foundations, Minkowski's 4-dimensional spacetime and the loaf it implies, the Lorentz transformation that mixes space into time, the relativity of simultaneity written as an equation whose offset grows with distance and speed, the invariant interval that all observers share beneath their differing slices. We watched the tilt become technology, the 38 microseconds a day that GPS must cancel, the 11 kilometers of drift it prevents, the flown atomic clocks of Haffler and Keating coming home disagreeing. We watched gravity curve the slices near a black hole and drag them around a spinning Earth, measured by gravity probe B to the width of a hair seen from 10 miles off. We watched Gödel's rotating universe threaten to erase the global now entirely. And we watched the quantum world stitch reality together more tightly than any local slicing allows, confirmed by loophole-free Bell tests and honoured by a Nobel Prize, while never once permitting a signal to cross the gap. Here is what the evidence has shown. The relativity of simultaneity is beyond dispute. There is no universal present, and the now genuinely tilts. The block universe is the cleanest reading of that fact, but Stein's theorem proves it is not forced. Relativity's symmetries support only a local present, not a real global slice. Presentism survives only by positing an undetectable preferred frame, judged extravagant by most physicists, yet strangely echoed by Bell's suspicion and by the non-local correlations we have measured. Conventionalism holds a genuine truth about the unmeasurable one-way speed of light, narrowed but not killed by malament. And whether the cosmic microwave background even provides consistent standard of rest is, right now, in tension with the data. What remains open is the deepest thing of all. Not how the now behaves, we know that with breathtaking precision, but what the now is. Whether the loaf is finished, laid out complete from first light to last, or still baking, its future edge genuinely unwritten. Or never a loaf you can slice at all, only the local point where you happen to stand. Physics has drawn the boundary of that question with great care. It has not answered it, and it is honest to say the equations do not yet reach that far. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds, and it costs you nothing but a moment. And if the question of whether the future is fixed or open stays with you, if you find yourself turning over what it would mean for time to have a direction at all, when the underlying laws run the same forwards and backwards, there is a related exploration waiting on the end screen and in the description, following that same thread of time's arrow a good deal further than we could here. You live every second inside a slice of a structure you cannot see whole, a present that is yours alone, tilted against everyone else's, resting on a geometry so precise it holds the world together, and so deep that it will not yet tell you whether the moment you are in is the only one there is, or one slice among countless others already laid down in the loaf. I want to go back and deepen several threads before we truly close, because there are places where the science has more to say, and where the honest picture demands more care than a single pass allows. Return first to the invariant interval, because it carries a subtlety I glossed. When we say two observers agree on the space-time interval between events, we are saying something stronger than that they agree on a number. We are saying they agree on the causal fabric, on which events can influence which. Consider the notion of proper time, the time measured by a clock carried along a world line itself. It is the interval computed along your own path through space-time. And it is invariant. Everyone, whatever their frame, agrees on how much time your own wristwatch registered between two events on your life. Alice and Bob disagree about the now in Andromeda. But if Alice flies to Andromeda and back, everyone in the universe agrees exactly how much she aged on the trip. The tilt reshuffles the shared now. It never touches the private clock. This is why the relativity of simultaneity produces no paradox for any single life. Your own becoming, the accumulation of your own proper time, is frame-independent. What is frame-dependent is only how your becoming lines up with a distant stranger's. Picture two hikers crossing the same mountain range by different routes. They disagree about how far north any given ridge lies, because each measures north from their own heading. But the length of the path each actually walked is not in dispute. Proper time is the length of the path you actually walked through space-time, and no one can argue you out of it. Now deepen the growing block, the view we have so far only named. Broad in 1923, and later Michael Tooley, proposed a middle path between the static loaf and the fleeting present. The past and present are real, accumulating, but the future is not yet real. The loaf is real up to its growing edge and nowhere beyond. It is an attractive picture because it honors both the fixity of the past and the openness of the future, the two things our experience insists on most. But weigh it against the relativity of simultaneity, and the strain shows immediately. If the loaf grows, there must be a growing edge, a global now that is the boundary between the real past and the unreal future. And relativity tells us there is no global now. The edge would have to be a tilted, frame-dependent slice, which means one observer's real past would be another observer's not yet real future. And the two accounts could not both describe a single objective boundary. Which slice is the growing edge? The theory refuses to say, because it refuses to privilege any slice. The growing block wants an objective present to be the edge of reality. Relativity denies it one. So the view, elegant as it is, inherits presentism's deepest problem. It needs a preferred slice the physics will not grant. Consider an analogy from the everyday. Picture printing press producing a long scroll, line by line, the printed past accumulating below, while the blank future waits above, and a single printhead marking the boundary. That image is the growing block, and it feels exactly right until you ask where the printhead is when different observers, moving relative to one another, each insist it sits along their own tilted line. There cannot be one printhead at two tilted positions at once. The scroll's neat, single, advancing edge is precisely what relativity forbids. The past feels fixed and the future feels open, but the physics offers no objective, universe-wide line where the one becomes the other. And this is where I find the whole subject at its most quietly unsettling and worth saying plainly. The two features of time that seem most undeniable from the inside, that the past is settled and the future is open, and that there is a single moving now we all share, are exactly the two features the physics most firmly declines to underwrite. Not refutes, declines to underwrite. Relativity does not prove the future is fixed. It proves that no shared, objective, universe-wide present marks the boundary between fixed and open. Stein's theorem then tells us the only present relativity's symmetries do support is the strictly local one. Here, now, the tip of your own light cone. What does it mean that the two things you are most certain of about time may be facts about your vantage point rather than facts about the universe? The science does not close that question, it sharpens it to a fine point and hands it back. Turn now to the arrow of time, because it is the other great puzzle the loaf leaves standing, and it deepens the open edge. The fundamental laws, the equations of motion in mechanics, in electromagnetism, in the quantum theory, are very nearly symmetric under reversal of time. Run them backwards, and they describe an equally valid physics. And yet, the world we inhabit is emphatically not time-symmetric. Cups shatter, but do not reassemble. Heat flows from hot to cold and not back. We remember the past and not the future. The block universe, taken at face value, treats past and future as equally real directions in the loaf, no more distinguished than left and right. So why is there an arrow at all? The leading account points to entropy and to the extraordinarily low entropy state of the early universe, the so-called past hypothesis. Given a universe that began in a state of very low entropy, the statistical drift toward higher entropy defines a direction, and that direction is what we experience as the flow from past to future. Consider a deck of cards, fresh from the box, perfectly ordered. Shuffle it, and it disorders. Shuffle again, and it stays disordered. Never in any human lifetime does shuffling restore the factory order. Not because it is forbidden, but because ordered arrangements are vanishingly rare among all the possibilities. The arrow of time, on this view, is that same statistical slide, scaled to a cosmos, anchored to a beginning of remarkable order. But notice what this explanation does and does not do. It grounds the arrow in a boundary condition, the low entropy early universe, rather than in the laws themselves. And it leaves untouched the deeper question of why that boundary condition held, why the early universe was in so extraordinarily ordered a state to begin with. Here, the science reaches a genuine limit. It can trace the arrow of time back to the low entropy past. It cannot, from within the equations, say why the past was arranged that way. Where a question is really about the ultimate origin of the order the universe began with, we have reached the edge of what the measurement and the mathematics can settle. And it is honest to mark that edge and not pretend to cross it. The block picture accommodates an arrow. It does not, by itself, explain the initial condition that gives the arrow its direction. That remains open. There is a further consequence of the tilted now that reaches into causality and determinism, and I want to be precise about it because it is easy to overstate. The Reed-Dyke-Putnam argument, in its original 1966 and 1967 form, was aimed not only at eternalism, but at determinism. Nicholas Maxwell later sharpened this reading. the reasoning runs. If the events on my now slice are fixed and real, and some of those events lie in another observer's future, then that observer's future is already fixed, since it is my present. Chain the slices together across all observers and the entire block appears determined. But Stein's theorem cuts this argument at the root as well. If there is no relativistically privileged global slice, if the only defensible present is local, then I cannot use my tilted slice to declare a distant stranger's future already settled, because my slice, extended out to them, is not a real boundary of definiteness. The inference from the now tilts to everything is determined depends on the same false premise as the inference to the block, that the global tilted slice is ontologically real. Take that premise away, as Stein's proof invites us to, and neither eternalism nor determinism follows from special relativity alone. They may be true. The physics of simultaneity does not establish them. Let me anchor one more piece of this in something concrete, because the abstraction of definiteness relative to a point can slip away. Think of a lighthouse keeper on a headland at night. Everything whose light has already reached the lighthouse, the ships that have passed, the stars whose photons have arrived, is, for the keeper, part of a settled past. That is, the keeper's causal past, the interior of the past light cone. Everything whose light has not yet arrived, and everything the keeper's own signals have not yet reached, is not settled relative to the keeper. It lies in the elsewhere or the future. This is Stein's local present made homely. What is definite for you is what could already have influenced you, and nothing further. Not a plane sweeping across the cosmos, a cone with its tip where you stand. Two keepers on two headlands, moving relative to each other, share no single now, but each has a perfectly well-defined causal past, and on that, remarkably, they never disagree. I return finally to the convergence that I find the most genuinely surprising thing in this entire landscape, the one I had never heard laid out this way until I followed the threads myself. Three completely independent lines of inquiry: the metaphysics of the flowing present, the foundations of quantum mechanics, and the interpretation of entanglement, each, when pressed hard, gesture toward the same forbidden object, a preferred frame, a hidden universal now, undetectable in principle. The presentist needs it to save the flow of time. The Bohmian may need it to guide the trajectories of particles. Bell suspected it beneath the non-locality of entangled correlations. And cosmology, in the cosmic microwave background, hands us something that looks tantalizingly like a cosmic standard of rest, while the number count dipole simultaneously casts doubt on whether that standard is even self-consistent. Four roads from four different countries of thought converging on the same undetectable landmark, and the surface geometry of relativity, tested to staggering precision, insisting the landmark is not there. That is the shape of the open question, and it is a far richer shape than the textbook slogan, "There is no absolute time," suggests. There may be no detectable absolute time. Whether there is an undetectable one, a now the universe keeps to itself and never reveals in any measurement, is not something the evidence has closed. It has, if anything, made the possibility more interesting than it was a century ago. And this is the point where the science, having done its enormous work, must be honest about its own frontier. It can tell us how the now behaves under motion and gravity to as many decimals as we can measure. It can tell us that no experiment has ever revealed a preferred frame, and that no signal ever crosses the gap that entanglement bridges. It can tell us that the block reading is clean but not forced, that presentism is possible but costly, that the local present is the only one relativity's symmetries endorse. What it cannot tell us, what lies past the edge of what any measurement can settle, is whether the present is the whole finished loaf, or a growing edge, or only ever the local here and now, or a relational bubble, or an illusion cast by records inside timeless configurations. That question touches the ultimate nature of existence itself, whether becoming is real, whether the future is written. And there the equations, for all their reach, fall silent. It is honest to say so, and to leave that silence unbroken, rather than fill it with an answer the physics does not license. Let me bring this exploration to a close. We began on a sidewalk, with two people passing in opposite directions and disagreeing, by days, about the state of the Andromeda galaxy, 2.5 million light-years away. From that single, ordinary image, we followed the tilt down into its foundations, Minkowski's four-dimensional spacetime and the loaf it implies, the Lorentz transformation that mixes space into time, the relativity of simultaneity, written as an equation whose offset grows with distance and speed, the invariant interval and the proper time that all observers share beneath their differing slices. We watched the tilt become technology, the 38 microseconds a day that the global positioning system must cancel, the 11 kilometers of drift it prevents, the atomic clocks of Haffel and Keating flown around the world and coming home disagreeing. We watched gravity curve the slices near a black hole and drag them around a spinning Earth, measured by gravity probe B to the width of a hair seen from 10 miles off. We watched Gödel's rotating universe threaten to erase the global now entirely, and the ADM formalism cut the loaf into a formal stack of slices. And we watched the quantum world, through loophole-free Bell tests and a Nobel Prize, stitch reality together more tightly than any local slicing allows, while never once permitting a signal to cross the gap. Here is what the evidence has shown. The relativity of simultaneity is beyond dispute. There is no universal present, and the now genuinely tilts, curves, and drags. The block universe is the cleanest reading of that fact and the physicists' working default. But Stein's theorem proves it is not forced. Relativity's own symmetries support only a strictly local present, not a real global slice. So the march from the now tilts to the whole loaf is equally real is a philosophical step, not a theorem. Presentism and the growing block survive only by positing a preferred, undetectable slice that most physicists judge extravagant. And yet, that same hidden frame is echoed, remarkably, by Bell's suspicion, by the preferred foliation quantum interpretations, and by the non-local correlations we have actually measured. Conventionalism holds a genuine truth about the unmeasurable one-way speed of light, narrowed by Malamud but not killed. And whether the cosmic microwave background even furnishes a consistent standard of rest is, right now, in real tension with the number count dipole data. What remains open is the deepest thing of all. Not how the now behaves, we know that with breathtaking precision, but what the now is. Whether the loaf is finished, laid out complete from first light to last, or still baking, its future edge genuinely unwritten, or never a loaf you can slice at all, only the local point where you happen to stand. And beneath even that lies the arrow of time and the ordered state the universe began in, a boundary the science can trace back to, but not from within its own equations explain. Physics has drawn the border of these questions with great care. It has not crossed it. And it is honest to say the equations do not yet reach that far. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds, and it costs you nothing but a moment. And if the question of whether the future is fixed or open stays with you, if you find yourself turning over what it would mean for time to have a direction at all, when the underlying laws run the same forwards and backwards, there is a related exploration waiting on the end screen and in the description, following that same thread of time's arrow a good deal further than we could here. You live every second inside a slice of a structure you cannot see whole, a present that is yours alone, tilted against everyone else's, resting on a geometry so precise it holds the navigation of the world together, and so deep that it will not yet tell you whether the moment you are standing in is the only one there is, or one slice among countless others already laid down, waiting in the loaf. Good night.